Hey there. You know, when you see water boiling for your coffee, you're actually watching this incredible battle of pressures happen right at the molecular level. It's pretty cool. But what if I told you that exact same process is the secret behind a super important lab technique called distillation? It's how we separate and purify all sorts of liquids. So today, we're going to break down both the science of boiling and the magic of distillation.
All right, here's what we've got on tap. First, we'll get into the science of what boiling really is. Then, we'll figure out why different things boil at different temperatures. After that, we're diving into how we use that knowledge to separate liquids with heat, taking a close look at the whole distillation setup. And to wrap it all up, we'll compare the two main types, simple and fractional distillation.
Okay, let's get right into it. The science of boiling. It's way more than just a bunch of bubbles. So what's really going on down at the molecular level when a liquid starts to boil? You know, a lot of people think it's the same as evaporation, but it's not. So what's the real difference between evaporation and boiling? I mean, they both look kind of similar, right? A liquid turns into a gas. But trust me, the how and where it happens is completely different, and it's a super important distinction. Okay, check this out. Evaporation, that's a surface thing. It's pretty chill. Think about a puddle drying up on a warm day. Only the molecules right at the very top of the liquid have enough energy to escape and turn into a gas. But boiling? Oh, boiling is a whole different beast. It's a bulk phenomenon. That means molecules throughout the entire liquid, bottom, middle, top, everywhere, get super energized and make their escape. That's where the bubbles come from. So to really get boiling, you have to think about this constant push and pull, a battle of pressures. First up, we have atmospheric pressure. Just imagine all the air in the atmosphere, all those miles of it, having weight. And that weight is constantly pushing down on everything, including the surface of any liquid. It's like an invisible lid holding everything in. But the liquid is fighting back. It has its own pressure called vapor pressure. This is the upward push from the liquid's own molecules trying to escape and turn into a gas. And when you add heat, you're giving those molecules more energy, so they push upwards even harder. The hotter it gets, the stronger that push becomes. And this is it, the main event. The boiling point is that magic moment when the liquid's upward push, the vapor pressure, becomes exactly as strong as the air's downward push, the atmospheric pressure. They're perfectly balanced. At that exact point, that invisible lid is blown right off, and bam, molecules can now escape from anywhere inside the liquid. That's what a bubble is. It's a pocket of vapor that formed inside the liquid and is now rushing to the surface. Right, so what actually changes a boiling point? If boiling is all about this pressure battle, why do different liquids boil at totally different temperatures? You know, water boils at 100 Celsius, but something like ethanol boils way down at 78. What gives? Let's dig in. Well, it basically boils down to three main things: how strongly the molecules stick to each other, how heavy they are, and even what shape they're in. Let's take a look at each of these. First up, we've got something called intermolecular forces, or IMF. That's really just a sciencey way of saying how sticky the molecules are. If molecules have strong forces, like in ethanol, they really cling to each other. You need a lot of heat, a lot of energy to pry them apart. But if the forces are weak, like in dimethyl ether, the molecules are barely holding on. It takes way less energy to get them to separate and boil. Look at that difference, 78 degrees versus minus 24 degrees. Okay, next up is molecular weight. This one's pretty intuitive. If you have two molecules with similar stickiness, the heavier one is going to have a higher boiling point. It's just like in real life, right? It takes more energy to lift a heavy bowling ball than a light tennis ball. Same idea here. It takes more energy to lift a heavier molecule into the gas phase. And finally, believe it or not, shape matters too. Specifically, branching. Think of it like this. Long, straight molecules are like perfectly cut logs. You can stack them very tightly together, with lots of surface area touching. This makes their connections stronger. But branched molecules are like tangled tree branches. They're bulky and awkward. They can't get close to each other, so their connections are weaker. Weaker connections mean less stickiness, and that means a lower boiling point. Okay, so we've established that different liquids have their own unique boiling points based on their stickiness, weight, and shape. So what? How do we actually use that information? Well, this is where we get into a really clever technique for separating liquids with heat. Let's introduce distillation. So what is distillation? At its heart, it's a technique for separating and purifying liquids. And the whole thing works because of what we just learned, that different liquids boil at different temperatures. We can take advantage of that, carefully heat a mixture, and basically boil off one component while leaving the other behind.
It's super useful. The whole process is a pretty neat three-step dance. First, evaporation. You heat the mixture and the liquid with the lowest boiling point turns into a vapor first. Makes sense, right? Second, condensation. That vapor travels through a cold tube, we call it a condenser, and it turns right back into a liquid. And third, collection. You just collect that now pure liquid, which we call the distillate, in a new flask. That's it. Heat it up, cool it down, and collect it. All right, let's head into the lab, virtually of course, and take a look at the equipment. We're going to go step by step through a typical distillation apparatus to see how all the pieces fit together. Okay, so here's the basic setup. You've got your heat source at the bottom and the distilling flask, which holds your liquid mixture. As you heat it, the vapor rises and the temperature is measured by a thermometer. This is super important because it tells you what's boiling. Then, the hot vapor travels into the sidearm and goes into the condenser. This is a tube with cold water flowing around it, which cools the vapor back into a pure liquid. And finally, that liquid drips down into the receiving flask. And there you have it, a purified liquid. Now, doing this in a real lab requires a few pro tips for safety, and just to make sure it actually works. First, don't fill the flask more than halfway. You need room for it to boil. And always use boiling chips. These little porous rocks prevent the liquid from superheating and bumping violently. Also, thermometer placement is critical. You want the bulb to be just below the opening to the condenser. Why? Because you want to measure the temperature of the vapor that's actually being distilled, not the liquid in the flask. And finally, use clips to hold your glassware together. You definitely don't want it falling apart mid-experiment. Okay, so distillation isn't a one-size-fits-all kind of thing. You've got to choose the right tool for the job. And the two main tools in our toolbox are simple distillation and fractional distillation. Let's break down when and why you'd use each one.
Simple distillation is exactly what it sounds like. It's for the simple jobs. You use this when the boiling points of the liquids you're trying to separate are really far apart. We're talking a difference of more than 70 degrees Celsius. It's basically one single cycle of evaporation and condensation. Easy peasy. But what happens when your liquids have boiling points that are super close together? That's when simple distillation just won't cut it. For those tough jobs, you need to bring in the heavy machinery, fractional distillation. And its secret weapon is an extra piece of glass called a fractionating column.
So here's how it works. That fractionating column is packed with something like glass beads or rings, which creates a ton of surface area. As the mixed vapor rises into the column, it starts to cool and condense on these surfaces. But here's the trick. The liquid with the higher boiling point will condense more easily and drip back down. The liquid with the lower boiling point will stay as a vapor and continue to climb. This process of condensing and revaporizing happens over and over and over again all the way up the column. Each time, the vapor gets a little bit pure. By the time it finally reaches the top and heads to the condenser, it's almost pure of the more volatile liquid. It's like running a dozen distillations all at once. So let's put it all together in a quick comparison. The use case? Simple is for big boiling point differences, over 70 degrees. Fractional is for the small ones. The apparatus? Fractional just adds that special fractionating column. And the efficiency? Well, simple distillation is like one round of separation. Fractional is like having many rounds stacked on top of each other, making it way more powerful.
So there you go. We've gone from the fundamentals of why a pot of water boils all the way to how chemists use that same principle to purify complex mixtures. And now that you know how it all works, think about this. This process is happening all around you on an industrial scale. It's used to refine crude oil into gasoline, to create perfumes, and to distill alcoholic spirits. So my question for you is, what else in your daily life depends on this incredibly powerful, yet elegantly simple process of separating things with heat?